Welcome back to the chapter about feeding. I'm now going to talk about major feeder disturbances that can be caused by the material. I will focus now on the disturbance and on the effect on the process. We will soon publish another course focusing on the specific material attributes that cause these disturbances. Let's start with the inconsistent mass flow. If the material sticks together and forms larger chunks, and these larger chunks fall out of the feeder, this can disrupt the mass flow rate, especially when feeding at low feed rates. This can significantly impact the concentration in the blend. Here you see magnesium stearate at a feed rate of 100 grams per hour. Since magnesium stearate is usually only used in ratios of 0.5 to 1%, this is very typical. Different options can help with such a problem. One can be to sieve the material before filling it into the feeder. This is a very common practice in pharmaceutical manufacturing. Another option is the installation of a screen at the feeder outlet. The screen is installed here. Here you see a screen that was installed in the feeding tests that you will watch later. These screens are available in different sizes and mesh shapes. As you can see in the video, the screen splits up the agglomerates and makes them smaller. This results in an equalized mass flow out of the feeder. Another widespread problem in feeding is the electrostatic charging of the material. Here you see a good example. As you can see, the material is even flying up against the gravitational force. A layer is formed on the equipment which can lead to blockage. Over time, more and more material accumulates. At the same time, this reduces the effective mass flow, hence the screw speed increases. Also, larger chunks can fall off at once, resulting in a concentration peak for this substance. Such effects are hard to counteract. To reduce this effect, it is essential to ground the equipment. The vessel from which you fill the feeder or other process equipment should either be grounded or directly connected to the equipment you fill via a conductive connector. There is also equipment available that should help to neutralize the charging by ionization. You might have seen that if you've used an analytical balance. The problem with such equipment is they offer narrow range of operation and it's hard to implement in the equipment. As an alternative, it is also possible to feed a pre-blend. The next feeder disruption that can occur is bridging in the feeder container. Here I depicted an example. The agitator that is installed in the feeder should counteract this effect. There are different types of feeders on the market with the agitator installed in various positions and different hopper designs, but the goal is always the same: avoid bridge formation and enable good filling of the screws. Nonetheless, something like this can happen. Here, a stable bridge is formed above the agitator. In such cases, manual intervention is often the only thing that helps. Vibration systems can also be installed, but they also disrupt the mass flow control, meaning a suitable compromise has to be found. This effect can be detected if looking at the process data. The screw speed will increase very early, much faster than it should, considering the container's fill level. It is therefore essential to compare the process data to prior tests to detect such an issue. You can detect this issue automatically and trigger a manual intervention if a correct model is implemented. This will avoid the significant mass flow rate decrease when the speed reaches close to 100%. This bridge formation can also occur in combination with a rat hole. This is a small channel in which powder is still flowing and the feeder performance stays at a decent level for some time. Then the screw speed increases and the mass flow decreases because the equipment cannot maintain the desired value. The countermeasures are the same as for bridge formation, manual intervention or a vibration system. Another effect you can encounter is the adherence of material to the screw. Here you see a picture of concave screws. They are self-cleaning, in theory, but very sticky material can form a layer on the screw which covers all the gaps between the two screws and between the screws and the housing. In this case, the transport of material was completely blocked. Usually, this problem starts gradually. As the free volume in the screws gets reduced, the controller will counteract by increasing the screw speed. But once the speed reaches the maximum, the mass flow will decrease. Here you see a few examples. In such cases, the only valid countermeasure is to stop the process and clean. This should be avoided by adapting the screw type or powder properties. Let's now look once more at the agitator. Here you see it from the top, in the feeder after a finished production run. The agitator also has another effect on the powder. It affects the residence time distribution. The material is mixed inside the feeder, which you can see in this simulation. You will be able to see the full video on the page below. Considering that the feeder is refilled frequently, the material is always mixed with new material. The easiest way to overcome this issue is to refill the feeder only with material from the same batch and clean it before changing to another batch. These were some of the major feeder disturbances that can be observed depending on the material. Check out the feeder videos for the different materials we provided for you in this chapter. With that, I would like to thank you for your attention.